Hello everyone, myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering in ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of optical communication, I am going to continue what we have discussed in the last lecture, that is point-to-point links part 2. In this we will have I am going to cover before you link budget and the rise time budget. In the previous class I have already told you that while designing any system in the optical communication, we take into account various type of analysis, so that the our system which is designed finally is more appropriate. So, these are the two type of data analysis. The first one is the link budget analysis and the second one is the rise time budget analysis. Now, what is the link budget? The optical power received at the photodetector depends upon the amount of light coupled into the fiber and the losses occurring in the fiber and at the connector and the splices. So, whenever we are about to receive the power from the at the end of the receiver section, we have to take into account all the system which are used in the construction of the optical fiber. For example, signal is generated from the laser, then our fiber, in between there will be connectors, in between there will be splices, each one of this contribute to losses of one or other kind. So, everything has to be considered into account when we are designing the optical fiber system. So, the link power budget is derived from the sequential loss contribution of each element in the link. Each of this loss expressed in the terms of decibels and it is given by 10 log P out upon P in. For example, here is one connector and here also optical fiber and here also optical fiber, and if we want to calculate the loss contributed by this particular connector, so this will be the P in for this and this will be the P out. So, P1 and if another connector is also added, in that case this P out of the first one converted into the P in for the second connector and P out. So, take it 1 1 and this as the 2 2. So, in that case we have to, if we want to calculate the loss, then it will be 10 log to the base 10 P1 out by P1 in plus 10 log to the base 10 P2 out upon P2 in. So, this will be the complete loss contributed by this two connector. So, each and every element is considered whenever we talk about the link budget. So, P in and P out are the optical power emanating into and out of the loss element respectively. So, this is one of the link budget point to point link for calculating the link budget. Here is a source transmitter section, here is a source, there is one connector, let it is contributing the loss LC. Then there is a fiber which is contributing the loss L alpha F. Then again there is a two splices and both of them are contributing a loss of LSP, and in between fiber alpha F. So, it is continuing and now it comes to the other part, again connector. So, each and everything is kept into consideration whenever we talk about the budget. Receiver section. So, what is the power emitted at this PT and what is received at the receiver, that is the PR, can't be same, because it has to be come across all type of losses which are in between these two. So, continuing with this, the link loss budget considers total optical power loss PT. The loss is contributed by the term PT, that is allowed between the light source and the photodetector. So, whatever loss is occurring is between the light source and the photodetector, and our light source in this case is either LED or the laser, because that is emitting the optical signal, and allocates thus loss to cable attenuation, connector loss, splice loss and the system and the system margin. Thus, PS is the optical power emerging from the end of the fiber attached to the light source, and PR is the receiver sensitivity. Then total loss is given by PT is equal to power which is emerging from the optical source and what is received at the receiver section, it is PS minus PR, and in between whatever type of connectors, whatever type of splices, whatever type of fibers loss, all are considered in this particular system, and a small margin is also taken into account, and it is taken as nominally it is taken as 6 dB, it is just a safety margin. So, these are the some description about the link power budget. And now we are going to do one numerical based on this for the better understanding of this topic. Let us see what the numerical says. In a fiber link, the laser diode output power is 5 dB. There is a fiber link and the laser diode output power is 5 dBm. So, what is the 5 dBm here? 5 dBm is the power which is emerging from the LED, that is our, as per the expression given here, it will be our PS. So, this will PS is equal to 5 dBm. Try to solve it parallelly. Source fiber coupling loss, that now a fiber is get coupled to the source, and when the coupling process occurs there is some loss, and this what is this loss now? It is 3 dB. Connector loss, connector is attached in between the fiber, because fiber has got a, if I have a fiber of 10 meter and we want to construct a, and the distance between the source and the destination is 30. So, what we have to do? How many connectors are required in between? So, 3 connectors, because we have a length of 10 meter only and the distance between the source and the destination is 30. So, in between we have to connect 3 connectors. So, this for that purpose connector are used. Connector loss of 2 dB and has 50 splices, that means it is saying that in the system which we have about to design is consisting of 50 splices, and each splices is contributing a loss of 0.1 dB. Each splices is contributing a loss of 0.1 dB. That means, when we talk about the 50, so it will be total loss contributed by splices will be equal to what? Will be equal to loss contributed by one splice, that is 0.1 into total number of splices, which is equal to 50. So, it will be a 5, and always remember that we have to write unit at the end. So, what is the unit? dBm. Fiber attenuation loss for 100 kilometer is 25 dB. It is given that fiber is also contributing to the loss, and the total fiber attenuation loss for 100 kilometer is 25 dB. Compute the loss margin for first APD receiver with a sensitivity of minus 40 dBm, that is PR is equal to minus 40 dBm. And for second case, hybrid pin-FET high impedance receiver of PR minus 32. So, you have to calculate the loss margin for two cases. So, first of all, we are going to, whenever we are about to calculate the loss margin, first we have to know about the PT. So, PT will be equal to what? Our PS minus PR, and when now PT get into account, and now PT will be equal to what? Different type of losses plus loss margin. So, first of all we are going to have a calculation of PT will be what? Source output power 5 dBm, so source fiber coupling loss 3 dBm, it is 3 dBm. Splicing loss is 5 dBm, every unit is dBm here. Fiber attenuation 25 dBm. So, total loss when we add, this is our what? This is our PR, PS, source output power, and this all are the losses. The total loss simply just add on and we will get this. Now, available power at the receiver is for the first one 5 dBm minus 35 dBm for the APD receiver. For the APD receiver is minus 30 dBm. So, now the loss margin is equal to minus 40 dBm, which is our APD receiver sensitivity, minus available power at the receiver, which will give the loss margin. And for the H pin FET high impedance receiver, receiver sensitivity is the minus 32 dBm, available power at the receiver is again minus 30 dBm. This will remain the same for both the cases. This value will remain the same because the receiver sensitivity varies, but the available power at the receiver will remain the same, and which is calculated by 35 dBm and 5 dBm. That is why 5 dBm is of course at the source output, and this is the loss. So, it is at the minus, it will be get minus 30 dBm. This is the available power at the receiver, which is same for both the cases, and the receiver's APD receiver sensitivity minus 40 dBm. Loss margin can be calculated by receiver sensitivity minus available power at the receiver. So, that is why minus 40 minus 30 dBm and will be equal to minus 10 dBm. Again in the next case, receiver sensitivity minus 32 dBm and loss margin, what is the formula? I think all of you are now aware of the formula here. Receiver sensitivity minus available power at the receiver. So, this will be equal to minus 30 to receiver sensitivity minus 30 dBm and it will be minus 2 dBm. So, in this way you will get across with various type of numerical. In some numericals it is ask something about the total loss which is occurring, about the receiver available power at the receiver, whatever, but these things remains the same. If the number of connector get increased, here we have taken into consideration only one connector, that is why it is 2 dBm. But if in any question it is asked to have a 3 connectors, so do you just multiply same as the splicing law. In that case we have to multiply this 2 dBm with 3 for getting the total connector loss. So, while solving any type of numerical, in this case of a link budget, first read out the question properly, what has been given and what has been asked. Now comes the rise time budget. So, what is the after rise time budget analysis is done only after the link budget. If the link budget is up to the mark, up to the our satisfactory level, then we will go towards the rise time budget analysis for the point to point link design. The rise time gives important information for the initial system design. Rise time budget analysis determines the dispersion limitation of an optical fiber. It determines the dispersion limitation of an optical fiber link and how it is calculated. The total rise time of an fiber link is the root sum square of the rise time of each contributor to the pulse rise time degradation. In this particular statement, what is going to be tell to you that when we are talking about the budget analysis, link power budget analysis, the previously we have studied about the power. That is why in every terms it comes the power, that is 5 dBm, 25 dBm in the terms of power, and dBm is the unit of a power. But here which type of analysis is the rise time budget analysis, not a power budget analysis. Sometimes students get confused between the power budget analysis and the rise time, but whenever it is asked power budget analysis, you describe the previous one, and whenever it is asked rise time budget analysis, then you comes to this. So, in this case also rise time of each one of the contributor same as the power is taken into account for calculating the total rise time of the fiber, and now it is taken the square of that, and after summation we take a square root. For example, there is a connector, there is a splices, of course fibers also contribute some extent to the rise time. So, all this are added, squared, and then it is square root has been taken. The link component must be switched fast enough and the fiber dispersion must be low enough to meet the bandwidth requirement of the application. So, in this case, for completing the bandwidth requirement which is used for the application, the link component must be switched fast and the fiber dispersion must be low. Adequate bandwidth for system can be assured by developing a rise time budget. So, what is the importance of the rise time budget analysis? For getting the adequate bandwidth for the system which we are going to design. As the light source and detectors have finite response time to input, the device does not turn on or turn off instantaneously. The rise time and the fall time determines the overall response time and the resulting bandwidth. So, now one more thing comes into account, that we are doing the rise time budget analysis because basically this determines the response time and the resulting bandwidth of the system. So, whenever it comes in the form of a notes, write the notes on the rise time budget analysis. So, you should also write about the importance, what is the significance of this one, that is for determining the response time and the bandwidth of the system. The connector, couplers and splices does not affect system speed, whereas in the last line it is told that light source and detectors have a finite response, the device does not turn off instantaneously. So, these are the major one, and connectors and couplers and splices does not basically affect the rise time as it affects only the power one. For basic element that contributes to the rise time analysis are transmitter rise time, group velocity dispersion rise time, modal dispersion rise time and the receiver. So, these are the major 4 contributors of the rise time. Always remember, couplers, connectors, splices does not contribute to the rise time, they only contribute to the power one. Now, the one by one we will discuss about the other parameters, the various contributor of the rise time and how much it contribute to the rise time. So, rise time due to modal dispersion is given by this one 440 upon Bm, which is equal to Bm is equal to B naught upon Lq, and it is L is the length of the fiber, Bm is the bandwidth, Q is the constant parameter which ranges between 0.1 to n1, B naught is the bandwidth of 1 kilometer length fiber. So, this one is the first contributor, that is modal rise time of the fiber. Now, comes the rise time due to group velocity dispersion, which is the second one in the list, and it is given by d square sigma lambda square L square, where d is our dispersion, sigma lambda is the half power spectral width of the source, and already we have known that it decides our dispersion spectral width of the source. It depends upon the which source we are using, whether it is LED or the laser. Laser have a narrow spectral width and the LED has a wide spectral width. So, our source, if we are using LED, our rise time due to group velocity dispersion will be different from whenever we are using the source LED or the laser, depends. Whenever we are using laser, it will be different than the when you are using LED. Receiver rise time will be equal to 350 upon beta Rx, where beta Rx is the 3 dB bandwidth of the receiver. So, and simultaneously the total rise time can be given by transmitter, dispersion, modal, receiver. So, these are the 4 contributor, first, second, third and the fourth contributor of the. So, for calculating the total rise time, what we are going to do? We take a square of each rise time. First is the rise time due to transmitter, we take a square of this, dispersion, modal, we are taking the square of this also, and the rise time receiver section square, and we take a square, and then after what we take a root of that. What is given here? We take a square of each of the contributor and then take a square root of that. This will be the formula for the total rise time, and the system bandwidth is given by, when you are able to calculate the total rise time of the system, based upon this we will able to calculate the bandwidth. That is why in the it is said that resulting bandwidth, it decides the bandwidth, response time and the bandwidth of the system is decided is based upon our rise time. Now, let us do one numerical related to the total rise time calculation. For a multi-mode fiber link, following parameters are recorded. LED with a drive circuit has a rise time of 15 nanosecond, and LED has given a spectral width of 40 nanometer already, which is given by sigma lambda, and this is our LED. That means it will be TTX. I think this is the notation TTX, that is transmitter rise time. Material dispersion related to time degradation is 20 nanosecond over a 60 kilometer link. Receiver bandwidth receiver bandwidth is given as 35 megahertz, modal dispersion rise time 3.9. So, let us have a look what is given in this particular numerical. TTX 50 nanosecond, T material 21 nanosecond, T mod 3.9 nanosecond, and what are the fourth major contributor, that is rise time of the receiver. So, we have to calculate this one, TRX, basically receiver ka we have to calculate about the TRX, that is receiver rise time, and as per the numerical it is given as 350 upon beta Rx. So, it is after calculating we will give this, and what is the total rise time of the system? Just get the square of each one and after that root. So, we have taken the square of 50 nanosecond, which is our transmitter rise time, material rise time square, modal rise time square and the receiver rise time square, and after that we will have a square root of that. So, we will get a total rise time of 30 nanosecond. So, in this particular class what we have discussed, the link power budget and the rise time budget analysis, which has to be taken into consideration whenever we are designing an actual system, actual point to point links in the optical fiber link, and this calculation are done prior to the actual implementation of the system. So, thank you for attending today's lecture.